So now for the coding part, we want to be able to solve for the three differential equations that we just solved for. So in order to do that, we need to first import numpy as np, and this allows us to do quick calculations to our code. Then we want to be able to import from the scipy library, so from scipy integrate library, so or area group, we want to import solve underscore IP, and this will allow us to solve for the initial value problem within the code. And then we want to use the scipy library again. Optimize module. We import root to solve for roots within our code. And now for graphing purposes, we're going to import flowy.io as PIO. This will allow us to change the graph's default settings. And then from flowy.subplots, the subplots module, we're going to import make subplots, and this will allow us to make subplots or make graphs within our code. And we want to right off the bat change the background of our graph from white to black, so we're going to go ahead and say PIO the templates default equals plotly. And let's see if this runs. Alright, so it runs. And now what I'm going to do is go off camera and write down all of our variables that are given to us, and then I'll be back to explain everything else. Now we have all of our variables defined here, and H equals 10 watts per meters squared per Kelvin stands for the heat transfer coefficient. R equaling 8.314 joules divided by mole per Kelvin stands for the ideal gas constant. Rho air, the density of air, is equal to 1.2 kilograms per meter cubed. The heat capacity of the air is 1,000 joules per kilogram per Kelvin. The heat capacity of the water in the gas phase is 2,000 joules per kilogram Kelvin. The heat capacity of the water in the liquid phase is 4,190 joules per kilogram Kelvin. And then the heat enthalpy of vaporization of the water is 40,700 joules per mole. And then from the Lewis relation, we can go ahead and calculate the mass transfer coefficient, which is the heat transfer coefficient divided by the density of air, which is going to be multiplied by the heat capacity of the air. And then the lowercase a at line 10 stands for the area of packing, the specific area of packing, which is in meters squared per meter cubed. MW stands for the molecular weight of water, which is 18 times 10 to the negative third kilograms per mole. M air stands for the molecular weight of air, which is 29 times 10 to the negative third kilograms per mole. And then if we were to use pitot2, we can see that the velocity is 5 meters per second of the water falling. And then the liquid flow rate is 0.5 kilograms per meters per second. And the pressure within the column is 101,325 pascals. And the height of the column is 20 meters. And then the temperature of the water, the feed water, so TW feed, is going to be equal to 70, which is given to us. But since all our units are in Kelvin, we want to add 273.15 to that value. and then the temperature of the air feed is going to be equal to 25, again given to us, and then we want to add 273.15 to keep the units consistent. And then this is going to be useful later on, but for plotting purposes, we want to make sure that all the points are equally spread for, again, plotting purposes. So we're just going to define our z plot, so z underscore plot is going to be equal to np.linspace, which is the function that allows us to make sure all the points are evenly plotted. We're going to use our start as 0, our stop is going to be the height, which is 20 meters, and then we want 21 points, and let's see if this runs. Okay. Now that we've defined all of our variables, now we're going to define a function. We're going to call this function PV, and our variable is going to be T. And what this function is going to be able to do is define or obtain pressures at a partial pressures at a given temperature, temperature that we decide to input. So what we're going to do is return the Antoine equation, which is 10 raised to the 8.07131, so 8.07131 minus 1730.63, and it's going to be divided by 233.426, and we're going to add the temperature variable in, and we're going to be subtracting the 273.15 because now we want to put it back in degrees Celsius. That's how the Antoine equation is written, so 273.15. And then we're going to close our brackets here. And we're going to go ahead and divide that by 760 times the pressure, which is 101,325 pascals, 325, and that's going to be our function. So outside the function, what we want to do is define our mole fraction of water in the feed. So we're going to say YA feed, and that's going to be equal to 0.5, which is the relative humidity, and that's given to the problem, 50%, times PV, which is the function we just defined, and inside the temperature, we're going to say TA feed, which is defined up here, 70 plus 273.5. And we're going to go ahead and divide that by our pressure, 101,325 pascals. And that should give us the mole fraction of water in the air. And then now what we want to do is define the gas flow rate of air, so G air, and that's going to be equal to the pressure times the molecular weight of the air divided by the ideal gas constant, 8.314 joules per mole Kelvin. So we can say R times the temperature of the air feed, so TA feed. And that's going to be multiplied by the velocity, V, which is 5 meters per second. And this should give us the gas flow rate of the air again. And then now what we want to do is go ahead and define our initial guesses for the initial value problem. So we're going to say Y out, and we're just going to define it as a guess. We're just going to say gas to clarify. Is going to be the mole fraction of water in the air, YA feed, times 1.1. And we're multiplying it by 1.1 because we want to, we know that as the air goes up, more water is going to be contained within the air. So we're just going to assume that it's going to be multiplied by 10% of the initial mole fraction of water in the air. And then what we want to do is do the initial guess for the temperature of the vapor, or the air temperature. So we're going to say Tg out underscore guess, and that's going to be equal to our dA feed, so air temperature of the feed, plus 5. And again, it's just a guess. That's why we're using plus 5. And the air temperature should go up as the temperature increases. So we're just going to guess it increases by 5. And then we're going to identify an empty variable. And this is going to be coming into play later on within the code. So we're just going to say sol equals none. Sol equals none. Let's just run that real quick, and that's good to go. Now that we've created a function that allows us to obtain partial pressures at any given temperature, we're going to go ahead and define a new function. And this function is going to be converging our initial guesses. Converge the values of the initial guesses. So define converge. And we're going to be using v2 as our variable. We will be using v later on. And so inside this function, we're going to go ahead and say our y out is going to be equal to v to 0. And our Tg out is equal to v2. And inside this function, we're going to also use a variable or a thing called global sol. So global sol. And what this allows us to do is modify variables outside of its current scope. So now we're going to be calling this sol variable out. And inside of this function, we're going to nest another function. So we're going to say define dy, tw, and tg with two variables, c and v. And what this function is going to be able to do is it's going to define the 3 differential equations that we already solved for on the whiteboard, and we're able to use the initial value problem solver to solve the equations. So we're going to go ahead and say y equals v0 is the first number in the array, tw equals v1, and tg equals v2. v2. Okay, and now what we're going to do is go ahead and calculate the gas flow rate of the water. So we're going to define GW, so it's equal to Y, which is the mole fraction divided by 1 minus the mole fraction, times G air, so gas flow rate of air, times the molecular weight of water, MW, times the molecular weight of air, M air. And then we're going to calculate the total gas flow rate, so we're going to say big G equals GW plus G air. go ahead and now define the total molecular weight. So big M equals the gas flow rate, total gas flow rate, divided by the gas weight of the air, divided by the molecular weight of the air, or that's the molecular weight of the air, and that's going to be added to gas flow rate of the water, divided by the molecular weight of the water, and then we're going to close that parentheses. So that's the molecular weight of the water. And now what we're going to do is calculate the heat capacity of the air, of the gas. So Cg is equal to C air, yeah, the gas, so the water plus the air. And we're going to say multiply that by G air and add CWG, which is the heat capacity of the water and the gas phase, times the gas flow rate of the water, and then close that and divide that by G, which is the total gas flow rate. And now we're going to define NW, which can be our molar flux of water. We've used this equation in our derivations of the differential equations on the whiteboard. We just have to redefine it in the code, and we're going to be using this later on, so it's just easier to define it as a variable. So we're going to say the mass transfer coefficient divided by R divided by Tg, R being the ideal gas constant, so it's capital R, Tg, temperature of the gas, times PV, which is PV, and that's going to be calling our function here. So we're going to be using the temperature of the water minus the mole fraction of the water times P, the total pressure. And now we're going to define our three differential equations that we have solved for on the whiteboard. So dy is equal to negative A area, packing area, times the total molecular weight divided by the gas flow rate, times the molar flux of water, so NW. And then our dTW, so now we're considering the temperature of the water. dTW is equal to specific area of packing divided by the liquid flow rate per area, divided by the heat capacity of the water in the liquid phase, multiply that by the heat transfer coefficient H, and that's going to be multiplied by the difference in temperature of the air and the water, so Tg minus Tw, and then we're going to go ahead and close that, and subtract that from our enthalpy of the vapor, so HV minus or times the molar flux of water, so NW. Close all that. And that should be good to go. And then now what we're going to do is define a third variable, which is going to be a third differential equation. So considering the temperature of the air, gas, which is the air, so TdTg is going to be equal to specific packing area A times the heat transfer coefficient divided by gas flow rate divided by specific heat of the gas, air, multiplied by the difference in temperature. So TG minus T. Okay. Next thing we have to do is return. And we want to return the three differential equations. So dy, dtw, and dtg. Alright. And outside of that function, the overarching function, which is convert feed air ty, using the variable v2, we want to return, or we want to use our sol function first. So we're going to say sol now equals sol underscore IVP, and we're going to use that IVP. So our function is going to be the dy tw tg. So our three differential equations. The time span is going to be from 0 to the height. And then our initial y value, we have to be really careful of this. We got to make sure that we use the out arrays. So we're going to say y out, tg out. Let's capitalize that. TG out. Or no, we want to make sure this lines up with TW, or the feed. Yeah, TW feed. So we want to call out the TW feed and TG out, TG out. And then we're going to use the method, which is going to be equal to none other than redo. And we're going to say our tenth output equals true. And then now we're going to use the return function. So return, we want to use the sol variable and create an array. So we want to use the first and last values in the array. So we're going to call those out and subtract it from the mole fraction of feed, air feed. So YA feed, and then we want to do the same thing. So we want to move to 1 now for the temperature of the feed. So, and then subtract that from again the temperature of the air of the feed. So TA feed. And what this return function really does is uses the solution from the VP, and it allows us to converge, gives us a function to converge with the initial conditions. And this first part is referencing to the mole fraction of the feed, and then this second part is referring to the temperature of the feed. And let's go ahead and see if this runs. And we have the first error, invalid syntax. So we can go ahead. Should delete that in the beginning. Okay. Seems like everything's running, but let's double check. Did I make any mistakes? Oh, colon. Did not have lowercase m there. With our function that's going to be used for converging our initial guesses defined and written out, we can now go ahead and use our root solver to solve for the roots of these equations. So we're going to use, it's asking for a function. We're going to find the overarching function converge via ty, and then our x naughts are going to be y out, and they're going to be initial guesses, and then tg out guess. And let's see if we, alright, y is not defined. Oh, that should be, there we go. tg out is not defined. What's the issue? We double booked that variable, so let's just make this one capital T. Alright, now it's right. KC, so I use lowercase k, right here, uppercase KC. Okay. Oh, okay. H, where's H? What did I use for H up here? Oh, lowercase h, capital H. Which line is it? Let's keep on solving with errors. Oh, maybe it's because I didn't use sol z plot, so sol, that's z underscore. Let's try running this. Hopefully. Hey. Okay, so I spelled method wrong. ME method. Alright, cool. Now we have our roots for this problem. And now what we can do is go ahead and begin graphing our solution. So we're going to add another line of code. So we're going to say fig equals make underscore subplots. Make subplots. We want 3 graphs, so we're going to say number of rows. There's going to be rows. There's going to be 3. Or OW S equals 3. And then columns is equal to 1. And then we want to do fig dot add underscore scatter. And here we're going to use S being our z plot, we defined above, y being the solution, so equal to sol, an array of 0 to the colon. And what the colon represents is all of the variable or all of the values inside the array. And then we want to name this plot YH2O. So name equal to YH2O. And then we're going to have row, have this be row 1, column 1. Let's see if this plots. Let's get one plot. Okay, so we have one plot occurring. Now what we're going to do is go ahead and copy and paste this twice. We're going to keep all this the same. We're going to change this to 2, and change this to 3, and change the names to TW and TG. Let's see what we get. Awesome. Alright, so we got our 3 plots here. We want to change the spacing a little bit, so we're going to go ahead and say fig dot update layout, and we're going to say width equals 600 and height equals 900. Let's go ahead and run that. Awesome. Okay, now we are showing the graphs in a proper array, and these graphs showcase our solution for the three differential equations. And this marks the end of exam 3.